Heron's fountain is dramatic and one of the best demonstrations of the topic liquids. A simply constructed, easy-to-make demonstration of the Heron's fountain is presented here. Its action is discussed on the basis of Pascal and Bernoulli's principles. But first, who is this Heron dude? And how does the fountain work? Heron is a Greek engineer and mathematician active in Alexandria between 60 and 70 AD. Just in case you don't know, Heron invented the first vending machine ever, aka coin-operated holy water dispenser. Yes, it's holy water, not Coke. And the never-ending goblet of wine. That could be a cool thing, but sadly, historian John Humphrey notes that this is a good example of a mechanism that was probably never constructed because it is difficult to understand how the goblet could actually be drunk from. Back to the fountain, it works and we will show you how. Heron's fountain consists of three parts: an open basin A, an airtight water supply B, which contains only water initially, and an airtight air supply C at the bottom. To set it up, we run a pipe from a hole from the bottom of A to C, another pipe from the top of C up to near the top of B. A pipe should run from almost the bottom of B up to the bottom of A. Heron's fountain is a mechanism based on air compression and the incompressibility of water. The mechanism works like this. First, water comes down through an outlet and pressing the air. The air in turn presses water, pushing the water to exit. So, how to start the fountain? Well, just pour some water in A, and voila! We have the Heron's fountain running.
The water from the basin A flows by gravity into the bottle C, which was originally filled with air. The water fills container C and displaces the air inside C, reducing the hydrostatic pressure P2 equals to rho GH2, additional to the initial atmospheric pressure PATM. As a result of the pressure, forces air up to the upper vessel, and according to the Pascal's principle, the air transmits this pressure to the water in the upper vessel B. The pressure that the air exerts on the water in the vessel B opposes the atmospheric pressure and the hydrostatic pressure P1 equals to rho GH1. Thus, the compressed air inside vessel B and C forces the water to spout out of the fountain's upper tube and drives the fountain. Heron's fountain is also a good demonstration for Bernoulli's principle. Let us consider again the fluid as an ideal, and determine the speed of the ejected water from the nozzle of the fountain. Use the Bernoulli's principle at the top of the water in the vessel B and the nozzle. The vertical motion of the top of the water inside vessel B is insignificant. Therefore, the vertical speed of water at the top of vessel B is negligible compared to the speed v of the emerging stream of water from the nozzle of the fountain, and Bernoulli's equation becomes this. Solving equation above for v, we will find this expression for v. Bernoulli's assumption is not exactly correct because real-life fluids are not in viscid liquid. We need to consider the viscosity which causes drag in this case. Moreover, the liquid in basin contains gravitational potential energy, and as it falls downwards, it uses the pneumatic pressure of the air in the air supply container to push the water in the upper fountain supply container. Once the water drops below the level of the outlet tube in the fountain supply, the Heron fountain will stop.